In this video here, we're going to be talking about the law of sines. Now, the law of sines is something that we can use for triangles to solve for sides or angles of triangles, and for any triangle, not just a right triangle. Now, the law of sines does apply to right triangles as well. It works for any triangle that's out there. But when you have a right triangle, basically what the law of sines becomes is the SOHCAHTOA definition: sine is equal to the opposite over the hypotenuse. So if you have a right triangle, you just use sine equals opposite over hypotenuse. That's what the law of sines would become if you had a right triangle. So what the law of sines says is that the lengths of the sides of a triangle are proportional to the sines of their opposite angles. All right, so in other words, sine of angle A over side A is going to be equal to the sine of angle B over side B, which is also equal to the sine of angle C over side C. Right, so we can use the law of sines if we know two angles of a triangle. Like, so let's say I know angle A and angle B, and if I know one of those opposite sides, either side A or side B, I could plug in angle A, angle B, and then one of those two sides, and then I can solve for that other side that I don't know about. Or if I know two sides, if I know side A and B, and I know one of those opposite angles, A or B, I can plug in the sides and whichever angle I know and then solve for that angle that I don't know about. All right, so I can use the law of sines to either solve for a side or for an angle. But in order to use the law of sines, what you need to know, let me step back a second. When you use the law of sines, you don't use all three of these at the same time. You only use two of them, right? So if I know things about angle A or side A and angle C or side C, I do sine A over A equals sine C over C, right? If I know things about B and C, I do sine B over B equals sine C over C. I don't use all three of these fractions together. I only use two at a time, depending on which sides and which angles I know, right? And then in order to use the law of sines, one of these fractions I have to be able to fill in completely. I need to plug in an angle and its opposite side, right? If I know any one angle in the triangle and its opposite side, and then if I know any other side or any other angle, I can use the law of sines to solve for the rest of the triangle. All right, so that's the law of sines. Again, it works for any triangle out there, not just for right triangles, although it will also work for right triangles. And we use it to solve for sides and angles, depending on what we have and what we're trying to find. All right, so that's the law of sines. Very important to know because it allows us to solve for angles and for sides when we don't have right triangles, right? When we have right triangles, we just use SOHCAHTOA to solve for our angles and solve for our sides. But we need to also be able to do that stuff for triangles that are not right triangles, and then that's where the law of sines comes in. And also the law of cosines, which is something I'll be doing in another video where I talk about the law of cosines. So I'm going to pause the recording here and then do an example or two where we use the law of sines to actually solve problems. Alright, so the problem here we're going to do: a satellite passes over observation stations in Phoenix and Los Angeles, which are 340 miles apart. When the satellite is in between the two stations, the angle of elevation is 60 degrees at Phoenix and 75 degrees at Los Angeles. How far is it from Los Angeles? Alright, so for this one, first thing I'm going to do is draw myself a picture. Just like with a lot of other word problems that involve trigonometry, it's a really good idea to draw a picture of what you're working with, just so you have that visual image that you can use. All right, so here's Los Angeles. Over here, we'll say Phoenix. I'm just going to put a capital P for Phoenix. And they are 340 miles apart. So the distance between them is 340 miles. All right, and then when this satellite is between the two, so the satellite is somewhere in that 340 mile stretch, but obviously up in the air. The angle of elevation is 60 degrees at Phoenix. So remember, angle of elevation is from the horizontal, so from the ground, 60 degrees upward from Phoenix, right? So here's my satellite. The angle of elevation from Phoenix is going to be 60 degrees, right? And 75 degrees at Los Angeles. All right, so that angle of elevation from Los Angeles is going to be 75 degrees, right? So there's my my picture that will for that is what we're doing in this problem. Sorry, I just completely lost the English language there for a second. So there's a picture that represents what we have working in this problem here. All right, so LA and Phoenix, 340 miles apart, and we know these two angles. So we've got a triangle here, right, between the two cities and the satellite. If we connect all three of those, that makes a triangle. We know two of the angles of the triangle, and we know one of the sides, right? So And we want to find how far is the satellite from Los Angeles. So we're looking for this side over here of the triangle, from Los Angeles to the satellite. All right, let me call this S up here for satellite. All right, so we were looking for that X distance there that I just labeled. All right, so to use the law of sines to solve this, and we're going to have to use, we can't use the SOHCAHTOA definitions here because this is not a right triangle, right? It's not a right triangle. It doesn't have any 90-degree angles, so I can't use, oh, sine is the opposite of the hypotenuse or cosine is adjacent over hypotenuse. That doesn't work here, right? Those things only work for right triangles that have a 90-degree angle. We don't have that here. All right, so our other option is the law of sines, which we just talked about a couple minutes ago, or the law of cosines, which is something I haven't done yet, but I'll be doing a video on that soon. So to do the law of sines, we need to know one angle and its opposite side. Right? Now that's not exactly what we have here. Right? I know this angle of 75 degrees at Los Angeles, but I don't know the opposite side over here. I know this angle is 60 degrees at Phoenix, but I don't know its opposite side. That's actually what I'm trying to solve for, where that X is. Right? I know this side here, the 340, but I don't know the angle opposite from that 340 miles. Right? So, but I can figure out this angle here. Right? So, in order to use the law of sines, I need an angle and its opposite side. If I know two of the angles though of a triangle, I can always solve for that third angle because all three angles of a triangle always have to add up to 180 degrees. Right? So if I add up the 75 and the 60, that's going to be 135 degrees, and then if I do 180 minus 135, that's going to be 45 degrees. Right? So I know now the angle at the satellite, between, looking from to Los Angeles and to Phoenix, that makes an angle of 45 degrees. All right, so now I know that angle and its opposite side. Now I can use the law of sines. Right? So, anytime you're doing a problem that involves, triangles, if you know two of the angles, you can always get the third angle. Sometimes you need it, sometimes you don't. If they had told us this distance over here between the satellite and Phoenix, we wouldn't need to know this angle because we could just use this side and its opposite angle. But since the only side we know is the one down here, we need to know that angle up there, so we use the fact that they all have to add up to 180. All right, and now what I'm going to do is actually erase the problem itself up here so we have enough space to actually do the work to solve the problem. It doesn't take a whole lot of work to solve it, but I just want to make sure we have plenty of space to do that. All right, so here's a triangle we have set up. So when you're doing these word problems, the first key thing is being able to draw a picture of what you have, label everything correctly, and doing all that stuff. All right, so now to solve for a missing side, I use the law of sines. Since I have this angle and its opposite side, I'm looking for this side, and I know its opposite angle. I can go ahead and set up the law of sines. So the law of sines says, if I do the sine of 45 degrees and put that over its opposite side, which is the 340 miles, that's going to equal the sine of 60 degrees over its opposite side, which is the X, the distance between Los Angeles and the satellite that I'm trying to solve for. Right? And now I need to solve that equation up there for X. All right, so that is our setup here for the law of sines. Notice, when I've set up the law of sines, I don't use a 75-degree angle at all because I'm not concerned with this side of the triangle. Right? Like I said a few minutes ago, when we're doing the law of sines, it's always just dealing with two of the fractions. Right? We never set up all three together. If we have to solve for this side also, we would set up another equation where I'm solving for that side over there. Right? We don't try to do them all at once. Right? Because to set up the proportion here, we need just one single unknown. Right? I can't solve for two different sides at the same time. I have to solve for one side first, and then if I need the other side of the triangle, I set this up again, but solving for this side, and then I get the other one. All right? So there's our setup for the law of sines. Right? The sine of this angle over its opposite side equals the sine of this angle over its opposite side. And the ones you choose is just based on which ones you know. Right? Which angle and opposite side do I know? Those ones definitely go into one single fraction. And then what side am I trying to find? Well, I use the angle opposite that side, the 60-degree angle. Right? And the 75 degrees is basically useless at this point. The only thing the 75 degrees was useful for in this problem was we had to know that in order to figure out that this angle up here was going to be 45 degrees. Right? But once we set up the law of sines, we don't need that 75 anymore. All right, to solve this now, anytime you're trying to solve a proportion, when you have two fractions equal to each other, you cross multiply. The 340 is going to multiply up there, the X is going to multiply up there. So it's going to be X times the sine of 45 degrees equals 340 times the sine of 60 degrees. All right, so x times sine 45. So when you use the law of sines, this is basically, once you have that proportion set up, those two fractions equal to each other, your next step is to cross multiply. And then x times sine of 45, to solve for x here, I need to divide both sides by the sine of 45 degrees. All right, so I get x is equal to 340 times the sine of 60 degrees divided by the sine of 45 degrees. All right, and now I can type this whole mess into my calculator and get the result of this, the distance between Los Angeles and the satellite. All right, so first thing, my angles are in degrees, so I just have to check my mode on my calculator to make sure it's in degree mode. So you can see the third one down there, radian and degree. My calculator is in degree mode, so I'm ready to go there. So then I just type it in, 340 times sine of 60 degrees, close the parentheses, divided by the sine of 45, close the parentheses again. All right, so that's how I type it all in. Just make sure you're closing the parentheses on, after you put in those numbers for the angles, and then we get 416.4. So let's say that x is about 416 miles. All right, so this satellite is approximately 416 miles from Los Angeles at this precise moment, when the angle of elevation from Los Angeles is 75 and the angle of elevation from Phoenix is 60. Right? So this is actually an example of something they call triangulation. If you have two observation points and each one knows the angle to another point, or the distance to another point, you can triangulate that, make a triangle out of it and pinpoint exactly where that other thing is, based on the two observations. In this case, at Los Angeles and Phoenix, we know these two angles. We can say, oh, this thing is exactly 406 or approximately 416 miles from Los Angeles. Right, so it's a method known as triangulation. All you need is two observation points, and then the object that you're observing, those 3 points make a triangle, and then you can use trigonometry to figure out exactly where that point is. All right, so that's our first example here, doing the law of sines. Again, it's just setting it up, understanding what the law of sines says, which is not that hard of a formula to remember. Sine A over A equals sine B over B equals sine C over C. That's not that hard to remember. And then it's just a matter of making sure you set up those fractions correctly. Remember, you need one full fraction without any variables in it. So you need one angle with its opposite side, right? Whatever that is, in this case, the 45 degrees and the 340 miles, that makes up one of your fractions. And then the other fraction is going to be, well, whatever it is you're trying to solve for. In this case, we're trying to solve for side x. So I have to use the sine of its opposite angle, sine 60 over x. And then it's just cross multiplying and basic algebra, and then putting it into the calculator at the end to get your result. All right, so that's an example of the law of sines. I'm going to do another video now where I do a couple more examples using the law of sines. I'll do at least one where I use the law of sines to solve for an angle, which is similar but a little bit different when you're solving for an angle as opposed to a side. So make sure you check out that next video that I'm about to do so you can see some more examples of using this law of sines.